Brent. I'm an assistant professor here at the department. And I want to talk about a paper that we recently had accepted to IUI, the Conference on Intelligent User Interfaces, and it is called Automated Rationale Generation, a technique for explainable AI and its effects on human perceptions. So to get started, I want to talk a little bit about what exactly explainable AI is. So we say that an AI is explainable if it's able to reason about and communicate the motivations for its actions or its decision-making processes. Simple, clean, efficient. But why is that important? Why is that something that over the past few years has become more and more researched? And well, the reason is that, AI systems are becoming more and more complex, more sophisticated, and we're giving them more autonomy. And as we give them more autonomy, the likelihood that they do something that is unexpected or wrong increases. And when that happens, the idea is that explainability will kind of give this level of transparency between some human operator and the system, and that'll increase our trust in the system. So if it starts doing things that I don't understand, it's explainable, so it can tell me why it did the things that it did, and that's going to make me feel better. A little bit of a reductive view, in my opinion. But anyway, so as I said, there's more and more research on this topic over the past few years. However, even still, I think there are two main gaps in the research, and these are the things that I wanted to address with this paper, and the things that my co-authors wanted to address in this paper. And so the first of these involves explainable AI in sequential decision-making problems. And so I believe that sequential problems present a unique difficulty for explainable AI. And the reason I think that is, well, follow me on this. So let's say that I am a robot. Maybe I am, you don't know. But I exist in a sequential environment, and I've decided that I want to take the action, go forward. But I've done this. Now the question is why? Oftentimes in these sequential systems, how we make these decisions is we use local utility functions that tell us that one action is better than the other. So going back to my question, why did I go forward instead of back, or left, or right? I have some function that says, oh, there's a higher number there on going forward, so do that. Now let's workshop this. Let's unpack it a little bit. What this utility function is actually saying is that if you go forward, there is a possible future where you will get to some state or set of states that are really, really good for you. The problem with this is that I have no idea what those states look like. And it's incredibly difficult for me to figure out what states those are or why I want to be there just based on this utility function. And if I even wanted to start to do that, I would have to unpack all possible futures or all possible paths from that point to start to make sense of things. And that's really just scratching the surface of why this is difficult. Why it's hard to take a utility function and go, oh yeah, this is why I did the thing. But there's a second problem, and I think this is actually a critical problem and something that AI and computer science researchers kind of just struggle with. And that's the age-old question of why? Why? Or what? In this case, we know that we want explanations. We want them so bad. But what is a good one? How do I know when my explanation does the things that I wanted to do? If you remember back a few slides, actually, no, I'm not going to go back. On the bottom, where we say, oh, here's what the world will be like when we have explainable AI, that little guy is super optimistic. He says, oh, I'll be able to know from my explanation why you erred. I know how you made your decision. I know all of these things. And I think it's really stupid to assume that that's how it'll work. Because humans are going to be involved, and we are complicated, we are messy, and there are many human factors that you need to understand before you can even start to answer the question of, is this explanation useful? And these are factors that not many people are considering right now, which I think is ridiculous, because in order to make explainable AI more generally usable, these are factors that we have to consider. That's something that we wanted to do in this paper, was start asking these questions that nobody else really seems to want to ask right now. Okay, off my soapbox. So how do we do this? Well, We drew inspiration for our technique from a notable event that happened a few years ago, and actually was looking at the audience. Yeah, most people are probably familiar with this. And I am speaking, of course, about AlphaGo. So for those of you who aren't familiar, back in March 2016, Google, not really unveiled, but Google unleashed upon the world AlphaGo. It's an autonomous Go-playing agent, and it defeated in extraordinary fashion one of the greatest Go, or one of the best Go players in the world at the time, Lee Sedol. And these were all, you could watch these games as they were happening, and I know several people did. Like many AI researchers, many computer scientists, many hobbyists. It brought all kinds of people watching this event. And I was one of them. I did not get very much work done those days. I'm sorry, old boss. But while I found these games to be interesting, I was intrigued by some little maybe throwaway decision that somebody made when planning this event. That was these guys. Anyone know who these guys are? They were the commentators. They were the people that were calling the event. They would take the moves that AlphaGo did and try to contextualize them and make sense of why AlphaGo was doing what it was doing. And boy, were they horrible at it. So whenever AlphaGo did something that was unexpected, they would immediately go to that was a weak play. Why did AlphaGo do that? That is a mistake in its programming. Hooray for humanity. Everyone patted themselves on the back and felt really, really good. But then, flash forward 20, 30, 40 moves down the road. Oh, I get it. Wow, what a brilliant move that was. It was critical to AlphaGo's strategy. And that behavior was amazing to me. Because what was going on was these commentators were using their own decision-making process to make meaning out of something that they, I'm pretty sure, did not understand. They didn't know how AlphaGo worked, but they knew how Go worked, and they knew how they would play, and they were able to use that to create an explanation that worked for them, that made sense. And that is what inspired our whole approach, which is, why don't we use human decision-making and learn models of human decision-making so that robots or agents or whatever you want to call them can better explain themselves in sequential environments, so kind of circumvent the problem a little bit. So I've given a few talks on this before, and at a high level, we think about our approach as machine translation. Now, instead of translating between sentences of different languages, so translating English to French, we treat this problem as translating state and action information into natural language. And we do that using machine translation approaches. I don't want to go into too much detail on that, although I guess I have lots of time. We can talk about it later if you want. So we've had some past successes in this area. This slide that I've shown a few times before, we were able to train agents to play Frogger and train them using a corpus of semi-synthetic natural language, well, semi-synthetic language would be more correct, to generate these textual explanations for each move that it would make. Now, if you're reading these slides very, very closely, one thing you'll notice is, boy, that text sounds really kind of stilted, not like a person would say it. And you're right. Because we needed a ground truth to do our initial analysis, we used a grammar to generate all this language. Who knows something about grammars? Probably most people in this room. No matter how robust your grammar is, no matter how variable you try to make it, there is always going to be some amount of regularity in your grammar, almost like it's by definition. And what are machine learning algorithms really, really good at picking up on? Regularity and patterns. So as many reviewers accurately pointed out, that is a limitation of our previous approach. We didn't actually test this on actual human data. So one of the other things that we wanted to do in this paper was get rid of the grammar and show that this approach, this way of thinking about things, is applicable even on the chaotic, noisy, variable human data that you would need to train our approach. This is our lovely pipeline. Look at that. And we'll go through this step by step. First, I want to focus on step one, data collection. because this ends up being a non-trivial problem. So to train our system, we need to collect a training corpus of human behavior in a sequential environment, typically composed of state and action information. And then also we need natural language annotations, explaining why that person did what they did in this world. Well, lucky for us, human factors researchers are pretty well equipped to handle this. And one of the primary ways that they do this is they use something called a think aloud protocol. And so what a think aloud protocol is you have your researcher sitting in the same room with a participant, and they are doing some task. And all the while, they are thinking out loud about why they're doing what they're doing. They're trying to be as streams of consciousness as possible. However, what typically ends up happening is the researcher ends up acting like a big jerk and having to ask, why are you doing this? Why are you doing this? Why didn't you do this? Constantly prompting them to answer, why are you doing what you're doing? All of this to say, this is a very, very time-consuming and painful process, just all around. I don't like being that guy, and I don't like being asked why all the time. So what we needed to do in order to gather the requisite amount of data for our machine learning model is we needed some way to automate this. And that was our non-trivial data collection effort. So we had to solve this problem before we could solve the problem we wanted to solve. We came up with a pipeline now to do this. Our pipeline, even though this says three, actually consists of only two phases. The first one is just a guided tutorial that tells you, here's how you use our tool. And so it consists of two phases: rationale collection, where we have people engage in some sequential task. In our case, we're still having them play Frogger, so you play through Frogger, and you provide explanations while you're playing through Frogger. Then we move on to the last phase, which we call transcribed rationale review. And in this phase, we present you your replay. This is what you did. Here are the here are the explanations you gave. Do you like them? So it's one last opportunity for people to change what they've given us and really see their explanations in a larger context. Here's an example of our interface. So this is the interface for rationale collection. In this case, what would happen is every time the participant took an action, so moved Frogger around, we would pause the game, and at this point, their microphone would kick on. And we would ask them, hey, tell me what you're doing. The thought was that we didn't want them to type just yet. We want to get your gut reaction to why you've done this thing. After they do that, we used Google's speech-to-text API to transcribe their explanation. And at any point during this process, they can actually go in and edit it with the keyboard. After finishing the game, boom, we go to this interface. So this is the interface for the transcribed rationale review. And here, users have the ability to watch their entire replay, every action they took, and perhaps more importantly, every explanation they gave. And so if they, upon looking at this, decide that, oh, my explanation, I don't like how it looks in the greater context of my gameplay, they can change it here. And this is all incredibly key. Because we can't be there in the room prodding them constantly to get them to tell us stuff, this is the next best thing. We give them enough control over their data and their explanations that we feel confident in what they give us. All key. Now, once we have that training set, we use it to train an encoder-decoder network or a sequence-to-sequence network, same thing. Again, not going into too much detail there, but what you need to know is that the input is state and action information, and our desired output is natural language. So we have one more question that we really need to answer before we can send things through, which is, what does our state look like? In this work, we considered two potential state representations. The first one we called this complete view. The idea behind this is we wanted to try to learn, or see if we could learn, long-term decision-making tendencies. So can we learn how humans reason about long-term things? And the only way you could really do that is to give the entirety of the world as part of your state. To help reduce overfitting, we would randomly inject noise into this representation. However, there were some of the authors that thought that, well, in Frogger, you don't really need all of that. All of the decisions that you make in Frogger can really be boiled down to what's going on immediately around you. If I'm where Frogger is right now, which is on a log, I don't really need to know what's going on at the beginning of the level, at the bottom. So why don't we just take what's going on in a small box around Frogger and make that our state? And that was the intuition behind the focused view. So the idea here is that we should be really good at identifying the things that are going on around me, but maybe less good at long-term planning. So with all of this, we're able to train our sequence and find some really interesting things. So just that little change in representation ends up giving you drastically different explanations, or rationales, as we call them. It's not true explanations. In general, so some of these are kind of fun, but the general takeaway is that when using the focused view, your rationales are typically very short, however, very accurate. We got, I want to say, very few sentences that didn't make sense when using the focused view representation, whereas the complete view, the agent was a bit rambly, talked about things that maybe weren't important, and sometimes struggled to produce sentences that were syntactically correct. So I think the second one, the complete view, is a sentence that is just gibberish. I have to move forward because lanes get closer to the yeah, kind of weird. But my favorite out of all of these is the last one, because I think this one does a good job of encapsulating all of the differences that we saw in the data. So for the focus view, I had to move back so that it did not fall off. It's referring to a log here. Short, accurate, fantastic. Whereas the complete view, I jumped off the log because the middle log was not going to come in time, so I need to make sure that the laws, and laws here is actually a mistranscription from the Google speech to text. So they said logs, but it read it as laws anyway, are aligned when I jump all three of them. So here, an incredibly long explanation, one that if you were to look at the data this is associated with, is right, but it starts to give you more detailed information about the decision making and involves looking further into the future. And this is just from including more of the state. Super interesting. Anyway, so to evaluate this, we performed a within subject study across two groups, if that makes sense. So what we did is we compared our rationales generated using our approach, both of those state representations, against two other baselines. So the first baseline was just random. So we looked at our training set, we picked out a human explanation, and we just said, okay, this is it. This is our low bar. If we don't meet this, we're doing something very, very wrong. The second baseline was the upper bar, the high bar. We picked out what we considered exemplary explanations. And how we came to that conclusion is we as the authors would only explanations that there was a consensus, a unanimous decision that this is an excellent explanation for the current state. That's what we considered exemplary. And there were like 5 authors on the paper, so yeah, high inter-rater reliability. For each of these, and so here's an example of the interface that we saw. So for each of these, we would get groups of people to answer questions about these explanations or these rationales. Important to note, these people were all separated into 2 groups. One group would only see rationales generated by the focused view state representation. The other group would only view rationales generated by the complete view. So keep them separate. Yes, so what people would see is they would see a small clip of an action taking place in Frogger. And then they'd be given these 3 rationales or explanations about what's going on, and then asked to answer questions about each of these, or to be specific, rate their agreement with the following. And these questions, these statements were meant to start to help us get at what we felt were the key benefits or the key goals that you want to accomplish with an explanation. So confidence. This should make you feel more confident in the agent's ability to perform its task. Understandability. This should help you understand why the agent is making the decision that it makes. Adequate justification, does it make sense? And so they did this for each explanation. Oh, and then finally, and arguably the most important question, why? Why did you rate this thing the way that you did? And that's used for a qualitative analysis later on. What we found was interesting. Maybe not surprisingly, both of our approaches, both of our state representations are able to dramatically outperform random, as expected. Unfortunately, what we found is that we were not able to, well, by our definition, we were not able to perform similarly to the exemplary explanation. So there was a significant difference between how people rated exemplary explanations and how they rated our candidate ones. But one thing that you notice, in our case that all of our candidates are in the red, is that the size of the effect is actually relatively small. So we are approaching there. But for me, what the most interesting thing is if you look at the, can you see this? No, okay. If you look at the difference between the, how people rated the exemplary explanation and the candidate for complete view and focused view, that difference is significant if you compare complete and focused view. So the complete view representation is significantly closer to the exemplary explanation than focused view. And that ends up motivating another study that we do a little later. So this is the quantitative analysis. And arguably this is kind of the boring analysis. What I think is more interesting is this, the qualitative analysis. Ooh, here's familiar with grounded theory. Got one. So grounded theory is it is an approach to performing a rigorous qualitative analysis that involves creating codes. Typically, you sift through qualitative data, and you are trying to quantify phenomena that are occurring, and you do that by developing codes. And then you iterate on these codes until you reach some kind of consensus. For us, what we did was a modified version of this. And we were trying to identify what are phenomena that that affect how people respond to these questions. So what affects people's confidence in the system? What affects people's, how people feel they understand a robot's decision-making process? And we came up with the following codes. So these are the phenomena, these are the factors that we say most influence how people perceive an explanation. Contextual accuracy, intelligibility, awareness, relatability, and strategic detail. So now what I want to do is just go into, unpack each of the questions that we asked with respect to these and give some fun examples of some of the things that people said. We're going to start with confidence. So there are 4 factors that primarily affect confidence. So given an explanation, how confident are you in the agent's ability to perform its task? And those are the explanations: contextual accuracy, strategic detail, awareness, and intelligibility. And in general, each of these affects it in a way that you would expect. So for instance, the higher your contextual accuracy, the higher your confidence the higher your confidence in the system. So rationales that display recognition of the environmental conditions and adaptation to the conditions were positive influence. Whereas if we just stated the obvious, that's a negative influence. So here, this is one of the more straightforward ways that these phenomena affect our perceptions of explanations. Here, though, you get interesting things starting to happen. Human likeness. 3 factors that affect this: intelligibility, relatability, and strategic detail. Anything related to humans is just super tough. So what you find here is that people are a little all over the place. So take intelligibility. On the one hand, rationales with typos or spelling errors seem to be more likely generated by a human. Makes sense, humans aren't perfect. However, you can find yourself in situations where error-free rationales there's no way they can't come from a human, because there's no way that a computer would have the knowledge to really know what's going on. So what you start to see is in human likeness, some of these factors are a double-edged sword, indicating that we might need to do more work in trying to further unpack things. This is one that I like. So relatability. What we found is that people were able to see the agent as more human if they could relate to the explanation that was given. So if the explanation mirrors their own thoughts, they start to see it as, well, they view the explanation as more human-like. Interesting, yeah.
Who were your subjects?
We had, these are people on Mechanical Turk. So we had 68, I think, for this first study.
And did you have any sort of screening?
Yes, we did. We were screening for people that were in the, let's see, they didn't have to be in the US, but I think they might have had to come from like a US IP address. We were really trying to screen for like sociocultural factors, so people that were familiar with Western culture. Also, what else did we screen by? I can't remember all of them.
Familiarity with Frogger?
Yes. Yeah, you'd have to be familiar with Frogger to make this work. There are other things that we screened for as well, but yeah, a lot of things that we had to consider here. So the things that influenced adequate, whether or not people felt that the justification was adequate, or contextual accuracy and awareness. So at a high level, what we're looking at there is people want to see if the explanation makes it seem that your agent is aware of of its surroundings, what's going on around it. So under awareness, participant 11 rated the random rationale low because it showed no awareness of its surroundings. So by increasing that, you increase people's view that this is an adequate justification. I also found this one super interesting. So understandability, and recall that understandability is people's own perception of how well they understand the agent's decision-making process. So how much of this explanation peel back the curtain. Those are mainly influenced by contextual accuracy and relatability. And really, relatability is the one that's most interesting to me. So people felt like they understood how the agent was making decisions when it kind of mirrored their own decision-making, which makes sense. When we see ourselves in the other, we understand the other. So all of these give us some, they can give us some design intuitions about what makes for a good explanation. But even then, these aren't perfect. These aren't complete, so more work still needs to be done here. Round 2. So we performed a second study. But this one was mainly, we wanted to test the differences in representation and how those manifest in a quantitative and a qualitative way. So we repeated this study, but now people could only rate two explanations. One generated by our complete view state representation, and one generated by our focused view. And we asked different questions, trying to get at different things here. So what was the most important difference between these two to you? Again, still trying to get at this qualitative knowledge. But then we asked questions concerning confidence, how people would view the agent if it failed, and how people viewed the agent if it just made a mistake but was able to still complete its task. We put a lot of weight on the user to unpack these two questions, but really, it wasn't a good way to ask them otherwise. So what we found was pretty fun. Overwhelmingly, on questions that weren't the most important difference because you weren't really rating them, people prefer the complete view. They prefer the long, rambly explanations that show some hint of long-term planning. And so in the paper, we go through each factor again, and we do another qualitative analysis, but in the interest of time, although, I want to focus on this one, which is, what is the most important difference? So tell me what that is. And pretty uniformly, people would say it's the ability to reason about long-term things, the ability to see the grand scope of the problem. And this, I think, is incredibly interesting, because again, it gives us some design knowledge, things that we can take to help make better explanations that are more well received by users and actually do the things that we want them to do. So my final thoughts. What a long, strange trip it's been. Unpacking explanations is tough. So asking these questions of why or what, things that we don't normally ask, it's really, really hard, guys. But you get such fantastic insights when you do it. And I feel like you get things that we're going to have to do this work eventually anyway. If we want to create systems that can interact with people, we can't just understand the systems, we have to understand people. So complete view and focus view representations, they both have their place, they both do different things and they do them well. So for the complete view, we start to see some evidence of learning how to strategically plan, or at least look like you were strategically planning. For focus view, you hone in on contextual accuracy, and you do that super well. However, most people seem to prefer the complete view in practice, so that's something. And all of this comes back to, there's more than one way to provide explanations. Right now, AI has a very narrow view of what an explanation is, but I think it's important to consider alternatives, because they have their place, and when it comes down to it, it's going to be the humans that really end up deciding what's useful. So, might as well start considering them now. And that's my talk. Questions? Questions? Yes.
You're using actual responses and discussions to actual people.
Yep.
These weren't generated by a program that was trying to solve it.
Nope, these
So
are not.
I'm wondering how this would apply to, well, the hard next step is getting a program to give any explanation whatsoever. And I mean, if it's going to help kind of, you say, well, it seemed like a good idea at the time, that's why I moved forward. Not very helpful. If it's based on some neural network, it'll say, well, this gave me the highest value of my objective function, and that's all I can tell you. How do you get around that problem of actually generating something more than the generic, it looked like a good idea at the time?
So, I mean, that's why we use people. So we're not necessarily, so that's actually one of the key differences between this and a more classic understanding of explanation. We're choosing not to tell you how exactly the neural net is making a decision, except because we're looking at reinforcement learners most of the time. Because we say, okay, that's one, really, 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 really hard, and even if you could do it, it might not really be helpful. So we're focusing more on tasks. So a better example might be if I'm classifying images, and I say that this image has a dog in it, we would go and ask people, okay, why do you think that there's a dog in this image? They would say, oh, well, I mean, look, this thing right here, point to some area, this is a dog. And so what we would learn is how to connect that image to what that person said, this is a dog. And so we're not necessarily saying that, oh, well, the third layer of my V4 neural net that had this output, and thus I made this decision. We're trying to get something human understandable by just going to humans. Now, if all of our humans said, oh, well, it seemed like it'd be a good idea, then we're kind of out of luck. But for right now, we're trying to focus on tasks that are well understood enough by people that they're a good source of information for us.
So if you have a machine learning problem,
Yep.
then maybe it will use one of these responses that you captured before.
Yep.
Now, why did you move forward? Oh, because there was a red truck coming in.
Exactly. And that's one of the things that we see. Actually, that's one of my favorites because the system doesn't know what a red truck is, but it learns it because it sees enough examples of people saying, yeah, this is a red truck. So it's also learning some really interesting, semantic information out of the stuff that we give it. Okay, I'll start over here. I'll just go this direction.
Okay, so do you think that when you take the problem jointly, so taking the decision and finding the most explainable decision, so do you think that it would make sense to have two different alternatives? So one is to take a suboptimal decision, which is more explainable, but the other one is make an optimal decision, but explain it differently so it's more understandable.
Oh, that's super interesting. That's super interesting. So I haven't considered that yet, but I can see that being incredibly useful.
Like a story.
Right. If given the choice, I can make a suboptimal, in a situation where I can reason about my actions a little better than we currently can, I'm going to make an action that, I know I'm going to have to do something that a human is not going to expect, no matter what I do. So instead of choosing the optimal action, I'm going to choose one that's good, but that I can explain better. I think there could be a lot of potential there, yeah.
So basically you have a two-criterion problem.
Right.
And you're just weighting the explainability.
Yeah, explainability versus optimality. So depending on the situation, some might be more preferred over others. This, of course, begs another question, which is how do you identify those situations? Back to people we have to go. what are people going to prefer at any given time? I don't know. Yes?
As this because I assume Frogger's an obvious because it's not that complicated, right?
For people.
Exactly. As the complexity goes up, though, don't you see the problem where, because how many participants do you have?
So for what? Oh, probably for the data collection.
Yeah.
We got 60, and those 60 generated about 2,000 pairs.
And that's the problem. Do you see the problem with as this complexity gets kind of, I mean, Frogger is a great game to start with, it's like maybe Go and stuff, where maybe it would be, how many more people you have to get as the complexity goes up.
Yeah, so yeah, scalability is an issue, and it's an issue that we don't understand very well. But my intuition, what it tells me, is that really your problem is not at that point the machine learning. Your problem there is people.
Yeah, you don't have enough humans actually.
Not even necessarily that you don't have enough, but it's, well, I guess it does come back to, but yeah, you have to find people that have the expertise to do the thing that you want. So why can't we do this with Go?
There's not many Go players.
Because yeah, there aren't many Go players. And of the Go players, like, how much of that game is done by, at this point, intuition and instinct? Like, a lot of them can't say, maybe they could tell you why they made this individual move, but Go is notorious for being difficult to evaluate the quality of states. So they just say, I do this because, like, I feel that this is going to get me where I need to go.
And another question, one of the AIs making one of those moves where it's so fast, so far ahead, if human couldn't even make it, how would they ever, if you didn't have a human that could ever explain how that move worked from where we are now, then could you never really explain it at all?
That's what I was going to counter with. It's like, if you have a move that a human can't explain, would you trust any explanation that a robot gave you?
Good question.
I have no idea. But my intuition says, well, it can go one of two ways. Either we put a lot of faith in the robot, and we trust everything it says because it's the computer and it's always right, or we're on the other side, and I'm not going to trust anything a robot gives me. I don't know how that works. So, yeah, it's hard. Yeah.
I still appreciate knowing more about motivation and when this can be used, and why we would even care about explanations.
Yep.
If I were to simply hire this seller, I guess, or whatever is the name,
Oh, yeah.
or the AlphaGo to play Go for me, I would hire AlphaGo without asking anything from the AlphaGo. I would simply, I wouldn't care why AlphaGo makes these moves. I just care about the effect, the result.
So,
And I think that that's the case in many situations in which we are. We really value experience and ultimate effects, and we don't necessarily care that much always about the explanation.
right. So, the situation that I use pretty frequently to motivate the need for this, so especially this approach, are in time-critical environments, cooperative environments, where failure is not necessarily a high cost. So you wouldn't want to use something like this in an environment where if you fail, everybody dies. So it's not going to be an autopilot. It's not going to be a bomb diffuser or anything like that. But imagine a situation where you and a robot are building a chair. And you are the human, you are kind of guiding things. You are determining how do I want to delegate tasks? How much do I want to trust my robot companion? If the robot is screwing up a lot and your trust erodes, you're going to take more of this upon yourself, and suddenly your efficiency just tanks. At least compared to being a truly cooperative problem. Whereas if you can start to trust your robot friend, even if it does make mistakes. So if it's able to explain, when people make mistakes, we explain ourselves and you go, oh, okay, yeah, I get it. Or, okay, just don't let it happen again, but that trust is still there. So that's the theory behind explanation. If the robot makes mistakes, and it probably will, but can explain itself, that trust should still be there. So you will still be willing to use it and still take advantage of whatever efficiency you can get out of it being a cooperative task.
But what if the robot giving an explanation that makes no sense to me?
Then, so at that point, explanations failed. And that's why, that's part of the reason we're doing all of this. We want to minimize the chances that our explanation fails. So even if the robot makes a mistake, at the very least it's able to justify its actions in a way that maintains trust and keeps that kind of cooperation going.
I'm sure there are more questions.
Oh, yeah.